Hello and welcome to this new video. In this video, I'm going to finish chapter 2 with section 2.3 about Galton-Watson processes. Okay, let us start with a riddle that may be asked in a job interview. Here's the riddle. An alien comes to Earth and the next day, one of the following equally likely alternatives happens. The alien dies. The alien replicates itself and dies. The alien replicates itself twice and dies. And finally, the alien replicates itself 3 times and dies. Okay. The next day, each new alien, independently of the others, reproduces itself according to the same pattern. Okay. The question is, what is the probability that the alien population dies out? Okay, let us try to analyze the situation. If xn denotes the population size at time n, and q denotes the probability that the population dies out, given that it starts from one individual, this is our unknown here, q. So at some time, the population will be 0. So this is the main unknown of the problem, because you start with one individual. But if you want to solve the problem, we have also to find the probability that the population dies out starting from any number of individuals. And I'll denote this probability by Q of k. Okay, so we have 2 probabilities, Q of k. So Q is a particular case. Q is Q of 1. Okay. Now, if the population has k individuals at a certain time, then the population dies out if and only if all the k branches die out. But since the branches are independent, the probability of dying out starting from k individuals is the product of the probability of each branch. Okay, so you may draw a tree if you like, starting from k individual. So we have 4 possibilities for each individual. Okay, so the tree repeats itself. Okay, so this is the first observation, is that Q of k is Q to the power k by independence. And now we use the conditional total probability formula that we used several times. So Q is what, actually? We condition on the first transition. Okay, so the Q is the sum of the probabilities of extinction. So there exists n such that xn equals 0, given that x1 equal k times the probability that x1 equal k starting from 1. Okay, and now this term is q to the k by definition. And in the riddle, this is just 1 over 4 because all the outcomes are equally likely. So we have 4 possibilities, 4 equally likely. In this context, of course. And so replacing q of k by q to the power k, I get 1 over 4 times 1, I factor by 1 over 4, so 1 plus q squared plus q cubed. So q satisfies a polynomial equation, q equal 1 over 4 times this polynomial. So if I multiply by 4 and subtract 4q, I get q to the q plus q squared minus 3q plus 1 equals 0. So this is the equation, you can call it the characteristic equation if you like, of the problem, that you have to solve in order to determine q. Now, this is a third order polynomial, so in general there's no formula, but here we observe the following, that if I put instead of q1, I get 1 plus 1 minus 3 plus 1, I get 0. So q equal 1 is a solution. And doing this, we do the Euclidean division, we divide this polynomial by q minus 1, and we get a second order polynomial that we can solve. If you solve it, you will find 2 roots. minus 1 plus radical 2, sorry, yeah, minus 1 plus radical 2 and minus 1 minus radical 2, or radical 2 minus 1. Now, so we have three solutions actually. Q equal 1, Q equal radical 2 minus 1, and Q equal minus 1 minus radical 2. Now, of course, we eliminate this solution because it's negative. So we are just left with two solutions. So how to decide which one we should choose, Q equal 1 or Q equal radical 2 minus 1? Okay, so this is a motivation to, this is a particular case actually of a more general theory. So such processes are called Galton-Watson processes or branching processes. And they were introduced actually by two mathematicians, Galton and Watson, in the 19th century as a model for the growth of the Lord's dynasty in the United Kingdom. So the problem was, what is the probability of extinction of the Lord dynasty? So we can analyze this more general problem actually in the same way. So if xn denotes the number of individuals of a certain population at time n, and we assume that at each time step, each individual produces independently of the others k offsprings, okay, with probability pk. In the riddle, we had p0 equal p1 equal p2 equal p3 equal 1 over 4. But this was a particular case. We can consider the more general this, okay, so we can have any probability distribution, okay, could possibly infinite. So the sum of pk's is 1. So if psi k to the n denotes the number of offsprings of the kth individual at time n, what can we say about xn actually? So we start with 1, but we can start with anything actually, but suppose that we start with 1. Then x1 is psi 1, so it's just the population number at time n equal 1, so after. And this probability actually, this random variable has distribution pk, okay? And then we do the summation. So xn plus 1 is the sum of all these. So sum all so at time equal n, we have, let us say, some number xn of individuals. And for each individual, we have a number of possibilities. Okay, so we sum all these random variables, independent random variables. So the stochastic process can be written in this way. Now, so all these psi kn are actually IID, and they have distribution pk. Okay, so I call psi a model random variable having distribution pk. Okay, so all psi kn have the same distribution as some model random variable that I call psi. Okay, so this is the distribution of all psi kn. So it should be clear that we have now a Markov chain on n, on the set of integers. So it's the state space is infinite here. Okay, so it's a particular case of a Markov chain, but it's a very particular Markov chain. So the main question is here is, what is the probability that there exists n such that xn equals 0? Okay, so the probability of dying of the population, of extinction of the whole population. So this is the main problem. And we are going to try to answer this question in a general context, in this general context. Okay. So we reason as in the riddle. So my unknown probability I denoted by Q, and Q of k is the probability of extinction starting from k individuals. So as before, Q of k is just by independence Q times itself k times. And I do the same reasoning that I did in the riddle. So Q is the conditional probability, And so if I apply the conditional total probability formula as we did, but instead of summing from 0 to 3, I can sum from 0 to infinity, because the reproduction process can have any probability distribution pk. Okay, so it must go from 0 to infinity. And by the same reasoning, we have, instead of a polynomial, we have a power series of k with coefficients pk, which are probabilities. So Q satisfies an equation. If I call this phi of Q, my probability, my unknown probability satisfies the equation Q equal phi of Q. And if you studied probability generating functions, you recognize that this is the probability generating function of the random variable xi. Okay, and that I will define it in a moment. Okay, so here's the definition. So I have to solve this equation, Q equal phi xi of Q. Now in the riddle, this was just a polynomial. Okay. So this is our main problem will be now, is to get as many information as possible about this equation. Okay, so definition. If xi is a random variable taking integer values with distribution pk, the probability generating function PGF of xi is by definition the mathematical expectation. So at the point s, which is variable, is the expectation of s to the xi. So it's something very close to the probability, to the moment generating function, fonction génératrice de moment, but instead of exponential e to the t xi, I have s to the xi. Okay. So by definition, it's this power series. Okay. So it's the sum of all values of s xi multiplied by the corresponding probability. So it's a power series about 0. And now we observe something. When you put s equal 1, you'll get sigma of pk, which is 1. So the series is convergent. Now we have a problem here, because when we deal with infinite series, we have the problem of convergence that we didn't have in the finite case. Okay? So we know from the theory of power series that if a power series converges at a point, then it converges for all values less than the absolute value of this point. So actually, I know now that this series converges for all s less than 1 strictly. So the radius of convergence is at least 1. Could be bigger, but for example, in the case of polynomial, it's infinite because it converges everywhere. So this is what we call Abel lemma, okay, that you studied in second year. So I know that this series is well defined on the interval -1, 1, and it's also continuous, because when s equal plus or minus 1, for s equal 1, I have 1, so it's convergent, and when s equal -1, it's also absolutely convergent, actually. So phi is analytic on -1, 1 and continuous up to the boundary. So we see that actually 1 is always a solution to the equation s equal phi xi of s. Okay, because when I put s equal 1, I get 1. So phi xi of 1 is 1. So we always have one solution. Q equal 1 is already a solution. Now, we don't know if the radius is strictly bigger than 1, but at any rate, we know that phi xi prime of s has a limit as s tends to 1. And we denote this limit by phi xi prime of 1. Okay, I will tell you why in a moment, why this happens. Because if you differentiate term by term, you get k pk sk minus 1. Okay. Now, this number actually could be plus infinity, actually. Okay, but anyway. So here are the properties of phi xi. So as we said, phi xi of 1 is always 1. Second property, phi xi of 0 is just p0, and it is pi of xi equals 0, because p0 is the probability that xi equals 0. So it's in our context, the probability that the alien or the individual does not reproduce itself. And that's it. So phi xi prime actually is the expectation. This is not difficult to see. And this expectation could be infinity, actually. So this is just a number between 0 and infinity. Okay? And if xi and eta are independent, then the probability generating function of xi plus eta is the product. You may know this for moment generating function, but it's still true for PGFs. Okay, this is not difficult. So first point, we already observe it, because the sum of the probabilities is 1. So phi xi of 1 is 1. By definition, phi xi of 0 is just the first term, the constant in the series. So and it's by definition the probability that xi equals 0. Now, we know that we can differentiate term by term inside the disk or interval of convergence. And we know that when s tends to 1, okay, here we can interchange actually limit and sum. Why? Because this series is of positive terms. So there's a corollary of the monotone convergence theorem that you studied in measure theory that tells you that we can interchange limit and summation, or limit and integral. Okay? So the limit of the sum is sum of the limits. Okay? And the sum of the limits is just kpk. And this is precisely the expectation of xi. Now, this expectation could be plus infinity, because I only have the convergence of sigma of pk, but I don't know if this series is convergent. Okay, if kpk, the series of general term kpk is convergent. Okay, so this could be plus infinity. Okay, and last term is just an easy consequence, because if xi and eta are independent, then any function of xi and any function of eta are independent. And so the expectation of the product is the product of the expectations for two independent random variables, as you know. Okay, so this concludes the proof of the first result. Now I need a technical lemma. The probability generating function of xn plus 1, which is a random variable depending on n, is the probability generating function of xn compounded with the probability generating function of xi. Xi is the random variable that models the reproduction of each individual. Okay, so in the riddle, xi took just 4 values, 0, 1, 2, 3, with equal probabilities. But here in this general case, it takes any integer values with probability pk. So it takes a value k with probability p sub k. Okay, why this is so? Okay, first notice that this is, so 1 of xn equal m, I should put brackets here, but this just to simplify the writing. This is the characteristic function of the event xn equal m. So at time n, we have m individuals. Now, you know from measure theory that the sum of these characteristic function is the characteristic function of the union, because they are disjoint. And since xn should take some value between, actually from 0, not from 1, this is from 0. So xn takes some value between 0 and infinity, actually finite, but we sum over all integers. So this is the whole space that I call omega, so which is 1. So this series of characteristic functions is 1. Therefore, I can write s to the power xn plus 1 as sxn plus 1 times this series is 1. Okay, so phi xn plus 1 of s is by definition the expectation of s to the power xn plus 1, which is the expectation of sxn plus 1 multiplied by 1. But now here, since I'm summing with respect to the index m, I can put the sxn plus 1 inside. Okay, because it doesn't depend on m. And now we can interchange summation and expectation by the dominated convergence theorem, because if I take the absolute value of this, it's less than 1 in absolute value, because s is between -1 and 1. Okay, so in absolute value, this random variable is less than 1. So it's integrable, because we are working on a probability space. So it's a finite probability. So the series of, so this is an integral actually. Okay, so the series of integrals of absolute value is convergent. Therefore, we can justify the interchange of integral and sum, or expectation and sum. Okay, so this is the first trick. Now let us consider each term. I go back to the definition of xn plus 1. It's the sum of all these independent random variables, and I do the summation. Actually, I should go from 0, not from 1. But it's not a big deal, but because, yeah. So we can go from 0 actually. So I think in the definition, no, I should go from 1, not from 0. Okay. Okay. So I just replace xn plus 1 as its function in terms of xn and this noise, these random variables. And now, since we are multiplying by the characteristic function of xn equal m, so I can replace xn by its value, right? Because if xn is different from m, then this is 0. Okay? So I can replace xn by m because we are multiplying by this characteristic function. Okay? And now, by independence, so xn, since xn is independent of xkn plus 1, so this is independent of this. So the expectation of the product is the product of the expectations. Now, the s to the power sum is the product of s, as you know. And the expectation of the characteristic function is just the probability of the event, as you know. So I just replace the expectation by the probability that xn equal m. And now I have a probability of a product by independence. It's equal to the product of the expectations. And now xi kn plus 1 is just an instance of xi. So I just can replace skn plus 1 by xi. And I get the product of the expectation of s to the xi by this probability. And now this is what? This is a product of a number times itself. This is phi xi of s. And it's multiplied by itself n times. So it's phi xi of s to the power m. And we are almost done. So now I just do the summation over m. And I see that here, what do I have actually here? I have a sum of a random variable multiplied by the probability that xn equal m. So this is by definition just, so if I call this element a, this is just phi of xi n of a, by definition of phi of xi n, because this is the probability generating function of xn. So it's by definition a power of what is inside to the power m times the probability. So it's just the composition of phi of xi n evaluated at phi xi of s. So everything follows from the definition. So this concludes the proof of this technical lemma. And now, as a corollary, if I apply this n times, I see that phi of xi n is the n-fold composition of phi xi. And therefore, I can permute. So instead of phi xi n of phi xi, I can also write phi xi of phi xi n, because this is just the n-fold composition. So you can prove this by induction if you like. And this is very useful. Now, remark that I will illustrate on with Python in the next video. If Q sub n denotes the extinction, the probability of extinction at time n, so the probability, unconditional probability that xn equals 0, then of course the sequence actually is increasing. So the sequence of events xn equals 0 is increasing, because if xn equals 0, then xn plus 1 equals 0. So it's an increasing sequence of events. And we know from measure theory that Qn converges to some limit. And this limit is precisely the probability of the union of xn equals 0, which is precisely Q, right? Because Q is the probability that there exists n such that xn equals 0. So it's the probability of the union of the events xn equals 0. So Qn is increasing and converges to Q. So I have now an algorithm for approximating Q by a sequence of events, by a sequence of probabilities. Okay? And now, so Qn is actually what? Qn is the first term in the probability generating function of xn, right? Because it's the constant term. So phi of xn here. So we see that Qn plus 1 is, which is precisely phi xi n of Qn, is precisely phi xi of Qn. Okay, so this is actually, if you put here Qn, you get here Qn plus 1. Okay, so I have now an algorithm for approximating Q. So I start with Q0, which is 0 actually. Q0 is 0. And then I iterate. I take Q1 equal phi psi of Q0, and Q2 is phi psi of, and so on. Okay, so it's fixed point iteration. And I shall illustrate this in Python, actually. Okay. So this equation follows from this relation here. Okay, remark, P1 is the factor of S in the power series expansion, actually. So it's P1. So it's the probability of Xi equal 1. Now, if P1 is 1, what happens actually? If P1 is 1, what does it mean? It means that with probability 1, each individual will reproduce itself one time. And in this case, we'll always have 1. So the sequence of the stochastic process will be constant. And this is not an interesting case. Okay, so we start with one individual. Next day, we'll have one individual, and so on. So this is an extreme case. It's not interesting. So it's useful to consider the general case where P1 is less than 1 strictly. It's more interesting. And here our main result about Galton-Watson processes. So we suppose that P1 is less than 1, and I call mu the mathematical expectation of Xi, the random variable of reproduction, right? So it's possible that mu equal plus infinity, as I said. Then you have two cases. If the mean value of reproduction is less or equal than 1, then the equation S equal phi xi of S has on 0, 1 a unique solution, which is S equal 1. And in this case, Q equal 1. So what does it mean? What is the interpretation? It means that if the mean value of reproduction is less or equal than 1 individual, then we are certain, so with probability 1, the population will die out. Okay? And this is not very interesting. Okay, so we are sure that, or with probability 1, the population will die out. Now, if the mean value of reproduction, so what does it mean? So mu is the average number of offsprings that each individual produces. Okay, so if the mean value of reproduction is bigger than 1, then the equation we want to solve has two distinct solutions on 0, 1, because we are seeking a probability solution, so we must work on 0, 1. So we have two solutions. One is always a solution, and another strictly less than 1 as 0, another solution as 0. In this case, so as 0 is strictly less than 1. And in this case, Q is necessarily the smallest root of the equation. Okay, now you may skip the proof if you like, because it's a little bit lengthy, but I will do it anyway. So, but you must understand what the theorem is saying and be able to apply it. We shall apply it in the exercises. Okay, so proof. So let us, for simplicity, write phi instead of phi xi. Okay, in the first case, the expectation of xi is less or equal than 1. What happens? For s between -1 and 1, we are in the disk of conversion, so we can differentiate term by term, as you observed. And we can differentiate another time. Okay? Now, phi double prime is non-negative, because everything is non-negative here. So we distinguish between two cases. Phi double prime vanishes at some point, and phi double prime is strictly positive. Okay, we are in case A. If phi double prime of s is 0 for some s, what does it mean? So I take this s, and I have an infinite series which is 0. So all terms are 0, starting from the index, from 2, right? Because if the sum of non-negative numbers is 0, then each number is 0. So kk minus 1, pk, sk minus 2 is 0. But since s is strictly positive, then and k is at least 2, so I deduce that pk is 0. Okay, in this case, what happens? In this case, phi of s just p0 plus p1 of s, because all the higher terms vanish. Okay, and by the way, the converse is true. Okay, so if phi of s is of this form, then phi double prime is 0, as you may check, because it's linear. And now it's very easy to solve the equation p0 plus p1 of s equal s, right? And the solution is s equal 1, right? If you solve the equation p0 plus p1 of s equal s, you'll get s equal 1. Now, the other more interesting case is that phi double prime is strictly positive. So phi prime is strictly increasing, and therefore phi is convex, strictly convex, actually. Now, by the mean value theorem, there exists a theta between s and 1, such that phi 1 of s, so theta depends on s, of course, for every s. So phi 1 of s minus phi s of s is phi prime of theta times 1. This is the mean value theorem. Now, since phi prime is strictly increasing and theta is less than 1, then phi prime of theta is strictly less than phi prime of 1, which is, as we said, mu, which is less or equal than 1. So phi prime of theta is less or equal than 1. So strictly. So this term is strictly less than 1 minus s. So phi of 1, which is 1, as we observed several times, because it's the sum of probabilities. So this is 1 minus phi of s, is strictly less than 1 minus s, and so phi of s is strictly less than is bigger than s. Okay, and therefore there is no other solution. Okay, because now is so s equal 1 is the unique solution of s equal phi of s, because for all other values, phi of s is strictly, so cannot be equal to s, right? If s is strictly bigger than 1. So this concludes the first case, where we have almost certain extinction. So we just look at the expectation of the random variable of reproduction. Okay, now the more interesting case, and by the way, you may draw a figure actually to illustrate this case. I will not do it now. I will do it in the next video in Python. Okay. Now, suppose that the mean value of reproduction is bigger than 1, and consider the function f of s equal s minus the PGF minus phi of s. If we differentiate, so phi prime is 1 minus phi prime, f prime is 1 minus f prime, and f double prime is minus phi double prime. And this quantity is less or equal than 0. But actually, we claim that this is strictly less than 0, cannot be 0. Why in this case? Let us prove this, that f double prime is strictly less than 0. If not, then phi double prime would vanish at some s, strictly between 0 and 1. And as before, we get that all the coefficients, all the probability will be 0 from k, starting from 2. So actually, phi is just a linear map. So therefore, what do we have? So we have mu is p1 is less or equal than 1, right? But we are assuming that mu is bigger than 1. Okay. So mu is what? Mu is 0 times p0 plus 1 times p1 plus 2 times 0 plus so on. Okay. So we have a contradiction. Therefore, f double prime is strictly less than 0. Therefore, f is strictly concave. Now, what do we have? F prime at 0 is 1 minus phi prime of 0. And we know that phi prime of 0 is the coefficient of s. So it's p1. So this is 1 minus p1. And we are assuming that p1 is less than 1, the interesting case. And f prime at 1 is 1 minus phi prime of 1, which is 1 minus mu. And this is strictly negative. It could be minus infinity. We don't care, actually. Mu could be plus infinity. So therefore, what do you have? You have a continuous function going from a positive value to a negative value. Therefore, it must vanish at some point. So it vanishes at some point, S1, and this point is unique because the function is actually strictly decreasing, right? So cannot have two solutions. Okay, so if this is negative, then phi prime is, yes, so phi prime is strictly decreasing in this case. Okay, go from 0 to 1 to something negative. Now, concavity tells me that at this point, this is what we call a critical point. This critical point is a maximum. Okay, so it cannot be a minimum, it cannot be a saddle point. Okay, so it must be a maximum, right? So in particular, f of s1 is strictly bigger than f of 1, and we know that f of 1 is 0. Okay, because f of 1 is 1 minus phi of 1, which is 0. And now we must distinguish between two cases. Phi of 0 equal to 0 and phi of 0 strictly less than 0. There are no other choices, actually. Okay. If f of 0 equals 0 and f of 1 equals 0, so it's like a parabola, actually. So f is concave. It goes from 0 to a maximum and goes back to 1. So we just have two roots, 0 and 1. But in this case, q equal 1 equals 0 necessarily. Because why? Because the population cannot die, right? Because p of xi equals 0 is 0. So there is each individual will reproduce at least one time, right? So cannot die out directly without reproducing any offspring. So the population will not die out. Okay. So the root is either 1 or 0, but cannot be 1, so it's necessarily 0. Okay. So we have two roots here, 0 and 1. Now, the last interesting case, f of 0 equals 0. So we go from a negative to a maximum, and then we go to 0. So we must vanish at some point. Okay, so we go from a negative value to a positive value. Therefore, there exists, by concavity actually, there exists a unique S0 at which f vanishes, and I call this S0. Right? So I will draw a figure in Python actually to make this more clear. Or you can try to do it yourself. So, and we just have to show now that the probability that we are seeking is just S0, the smallest root. Okay, so we have two roots, S0 and 1, and I take the smallest one. Okay, so let us use the sequence that I defined in a remark. So we start with Q0 equals 0, and then we iterate. And we know that Qn converges to the fixed point, right? So I claim first that this sequence that I defined inductively is strictly less than S0. And of course, for n equals 0, it's true because Q0 equals 0, so it's less than S0. And by induction, if Qn is less than S0, then Qn plus 1 is phi of Qn, which is strictly less than phi of S0, which is S0, right? Because f of S0 is 0, so S0 minus phi S of 0 is 0. So we have, okay, so it's a fixed point. So this proves the claim. And when I let n tend to infinity, I get Q is less or equal than S0. And this is less than 1. So I must conclude that Q equal S0. Okay? Because if Q was strictly less, so it's different, we know that Q is a solution of the equation Q equal phi of Q. So satisfy the equation. So it must be either S0 or 1. If it's not, if it cannot be 1 in this case. So it must be S0 because Q is strictly less than 1. Okay, so we have two solutions, S0 and 1, and Q is less or equal than the smallest one. So it's necessarily equal because it cannot be 1. So necessary Q equal S0, the smallest one in this case. Okay, so this concludes this video and chapter 2. Now, in view of the situation, actually, because this is really an exceptional year, and I think that you are all tired by now, I suggest that we only include chapter 0, 1, 2 in the exam. So I will not cover, so actually chapter 3 and 4 are very small. So I can cover them in maybe 4 videos. So just I need 1 or 2 weeks maximum. But I think it would be better to stop here at this point. So I will just do another video where I will solve the exercise of chapter 2. And this will conclude the course. Okay. Now, Poisson processes and Brownian motions are very, very important, especially if you want to work as an actuary. But I think in these conditions, so I don't have enough time to do that. So, but you can read them. They are in the notes. Okay. So thank you for attention and see you soon.